Dear students, today we will discuss the bonding situation in metal carbonyls. Bonding situation in metal carbonyls. What is the nature of bonding between metal and the carbon of carbon monoxide? Or we can say the nature of metal carbon bond. As we know that carbon monoxide molecule has a structure C, 2 covalent bond, 1 coordinate covalent bond. This oxygen is electron deficient, it is electron rich, so it fails to form bond with metal atom. It successfully form bond with the metal atom. It means the carbon of carbon monoxide form coordinate covalent bond with the metal atom. In carbonyls, the nature of bonding between carbon of carbon monoxide and metal atom, usually in zero oxidation state, is of coordinate covalent nature. The carbon monoxide group stabilize metal atom in low oxidation state, usually in zero oxidation state, due to synergic bonding effect. A metal carbon sigma bond is formed by the overlap of the filled sp hybrid orbitals of carbon of carbon monoxide and a vacant hybrid orbital of a metal. For example, in nickel tetracarbonyl, in which the nickel has zero oxidation state, the compound, this carbonyl is called tetracarbonyl nickel with oxidation state 0. Here, how the bonding is formed? This orbital overlap with this orbital, forming a bond, and the nature of bonding here remains almost same, not same, almost same, are M negative and oxygen with electron deficient nature. It is represented by A. In this case, the metal acts as Lewis acid. What is Lewis acid? Electron pair acceptor. And carbon monoxide as Lewis base, electron pair donor. Here pi bond is also formed by back donation of electron from metal to carbonyl group, metal to carbonyl group. How it is formed? Consider dx square y square orbitals, and these orbitals, the sign here shows that if it is crust, then it is crust. If it is trough, it is trough. That of wave. If we consider the wave nature of electron, the overlapping crust, trough form a pi bond. It means here the sigma bond was already present, now one pi bond is also present. This structure represented by B. The actual structure of this metal carbonyl is weighted average of the both resonance structures, the resonance contributing structures. These resonance contributing structures are A and B. The actual structure, a resonance hybrid, a real molecule, is weighted average of these two resonance structures. This sign shows that these two A and B are resonance contributing structures. How we get the evidence about the nature of the bond? The nature of the bond is decided by the bond length and infrared spectra. It means there are two evidences by which we can decide the nature of bonding. That is the multiple nature of bonding between carbon and oxygen in carbon monoxide, which has been coordinated with the metal atom in low oxidation state. Now, with the increase of back donation from metal to carbon monoxide, metal to carbon of carbon monoxide, the MC bond becomes short and stronger, and carbon monoxide bond become weaker and longer. It means M and C metal carbon bond become shorter and stronger due to back donation, synergic effect. And CO bond become weaker and longer. Longer bond is always weaker, shorter bond is always stronger. It means these resonance structures can be shown by the shifting of electron cloud as shown here. This electron pair shifts to here, this electron pair shifts to compensate the deficiency of oxygen on oxygen atom. So the other resonance structure is this one. So two resonance structures represents the real molecule by contributing to a certain extent. The dipole moment of MC bond is very low. MC bond dipole moment is due to polarity. It is very low, that is 0.5 d by, d means d by, it means there is almost no charge transfer. If there is big charge transfer, big charge separation, big polarity, then the dipole moment value must be very high. This value of dipole moment is due to the difference of electronegativity of M and CO. Metal accepts 2 electrons first from carbon of carbon monoxide and then donate 2 electrons back to carbon monoxide. So net charge transfer is 0. First, the metal accepts a pair from carbon of carbon monoxide, then metal transfer electron back to carbon of carbon monoxide. So net charge transfer is 0. Due to this net charge transfer 0, the dipole moment value is very low. The IR infrared stretching frequency for free carbon monoxide is 2150 per centimeter. Terminal carbon monoxide group in neutral metal carbonyls have stretching frequencies in the range of 2150 to 1850 per centimeter because from CO has because carbon monoxide has triple bond. Carbon monoxide has triple bond. When carbon monoxide reacts with a metal to form metal carbonyls, the CO bond order is decreased. The bond order of CO is 3. When it is free, not coordinated with the metal atom. Now its bond order decreased due to the back donation of the charge density from metal to carbon monoxide. More pi charge is shifted to carbon monoxide from the metal. Structure B become more predominant, which results in the decrease of IR stretching frequency of carbon monoxide. It means this B become more predominant, which results in the decrease of IR. It means the CO bond become of double bond nature instead of triple bond nature. Weakening of bond occurs and stretching frequency decreases. If charge density from metal is shifted completely to carbon monoxide, then bond order will be about 2. About 2. Not really 2, about 2. In fact, it is between double and triple bond. In metal carbonyls, IR stretching frequency of carbon monoxide depend on predominant contributing structure A or B. There are 2 contributing structures for the real molecule, a resonance hybrid, which are represented by A and B. For structure A, if the structure A is predominant, then IR stretching frequency will be about 2000 per centimeter. And for B, when B structure is predominant, it would be less than 2000 per centimeter. The unit of wave number is per centimeter. The approximation can be applied to explain the behavior and bond situation in various metal carbonyls. We will discuss next the explanation with real examples. Dear students, explanation of the situation of bonding in metal carbonyls is hereby explained by considering the real examples. In hexacarbonyl manganese, structure A, we have discussed the two contributing structures. So, among the two, the A is more predominant because of less shifting of pi charge from metal to carbon, which is due to positive charge on M. In chromium hexacarbonyl, infrared stretching frequency would be 2000 per centimeter, in which the structures A, B both are equally contributing toward the resonance hybrid, a real molecule. In vanadium hexacarbonyl, negative charge density has accumulated on metal, hence more charge is released from metal to carbon of carbon monoxide. This release of charge from metal to carbon monoxide results in predominance of contributing structure B. So its stretching frequency would be 1859 per centimeter. In titanium carbonyl, the titanium hexacarbonyl shows stretching frequency at 1750 per centimeter. It is because with the increase of negative charge on the metal, the stretching frequency further decreases. It means the nature of the metal, central atom involved, and the coordination number of the metal atom decides the strength of metal carbon and carbon oxygen bond in metal carbonyls. Thank you, students. Dear students, explanation of the situation of bonding in metal carbonyls is hereby explained by considering the real examples. In hexacarbonyl manganese, structure A, we have discussed the two contributing structures. So, among the two, the A is more predominant because of less shifting of pi charge from metal to carbon, which is due to positive charge on M. In chromium hexacarbonyl, infrared stretching frequency would be 2000 per centimeter, in which the structures A, B both are equally contributing toward the resonance hybrid, a real molecule. In vanadium hexacarbonyl, negative charge density has accumulated on metal, hence more charge is released from metal to carbon of carbon monoxide. This release of charge from metal to carbon monoxide results in predominance of contributing structure B. So its stretching frequency would be 1859 per centimeter. In titanium carbonyl, the titanium hexacarbonyl shows stretching frequency at 1750 per centimeter. It is because with the increase of negative charge on the metal, the stretching frequency further decreases. It means the nature of the metal, central atom involved, and the coordination number of the metal atom decides the strength of metal carbon and carbon oxygen bond in metal carbonyls. Thank you, students.